Hello, chemistry students. This is Professor Sean McMahon, and this is Chapter 10, Lecture 1, and I'll be discussing in this chapter chemical equilibrium. So to get started, to understand chemical equilibrium, we have to talk a little bit about chemical reactions and collision theory involved with chemical reactions. So during chemical reactions, collisions between our reactants must occur, and the bonds in these reactants must break so that I can form new bonds and produce new products. So this diagram is essentially showing me, here I have the two reactants colliding, breaking bonds. They have to be in the correct orientation, so they have to be aligned so that when these bonds break and they form new bonds, I can form the correct structures. So with collision theory, basically for reactions to occur, for me to break bonds and form new bonds, right? So my reactants, I break bonds, my products, I form new bonds. For this to occur, I have to have enough kinetic energy to break the original bonds, and I have to be aligned in the proper orientation to make the new ones. So this is just, again, an example of a reaction where I have nitrogen gas, oxygen gas combining to produce two nitrogen monoxide gas molecules. So if the collisions between the reactants do not have enough energy, then the bonds aren't going to break. So that's pretty much your criteria number one for collision theory. And really, we should be calling this effective collisions. So if there's not enough energy, the bonds aren't going to break because they're ineffective. So for the bonds to break, I have to have an effective collision, which requires enough kinetic energy to break the bonds. The other thing is, to have an effective collision, not only do I need the correct amount of energy, I have to have the right orientation. So they have to collide in a manner that's going to result in not just hitting with enough kinetic energy, but hitting with enough kinetic energy, breaking bonds, and simultaneously making new ones. So in this example, we see this is the incorrect orientation to produce my two products of nitrogen monoxide. This effective collision requirement, okay, this collision theory effective collision requirement is really referred to as activation energy. So activation energy is the minimum amount of energy required for a reaction to take place. And again, to reach this reactivation energy, I have to have the right orientation and enough kinetic energy to break bonds and form new ones. So here I have my reactants, here I have my products. Now we talked about this also in our thermochemistry when we talked about the difference between the reactants and the products as far as energy. We called that difference Q, or you can also call it enthalpy. And that enthalpy is the amount of heat required to bring it from this lower potential energy. So the reactants right now are at a lower potential energy than the products. But the activation energy is actually this peak here. And this is what we're focusing on. It's this entire amount of energy so that I can eventually form new bonds, become a little more stable, and then lower a little bit of energy. And with this activation energy difference, what we see is in this overall reaction, what we were studying before is that this is endothermic because it requires a positive amount of energy to go from our reactants to products. So this distance here is positive. So this would be an endothermic reaction or an endergonic reaction. So what's going to influence the rate of the reaction is a couple of factors. So we need an effective collision, and whatever increases the number of effective collisions is going to increase the reaction rate. The way we can measure the reaction rate is the amount of reactant used up in a given amount of time, or the change in concentration of product, so how much product is formed over time. So the rate of reaction is affected by a couple things: temperature changes, changes in concentrations, and the presence of a catalyst. So these are going to be things that affect those collisions in collision theory, where I have enough kinetic energy in the correct orientation for this to take place. So let's look at how temperatures can affect reaction rate. Typically at higher temperatures, molecules are going to be moving faster. When they move faster, they're going to have more kinetic energy. This increase in kinetic energy is going to increase my reaction rate. So an increase in temperature makes reactions happen faster. Why? Again, more collisions. More collisions means more molecules colliding and having that effective collision. So that effective collision is the correct orientation and enough energy to break bonds. So basically, more collisions increases that probability for an effective collision. So that's one of the reasons why we keep food in refrigerators. Why? Well, we want to slow the reaction rates to avoid foods from spoiling. Okay, so cooler temperatures slows down reaction rates. Higher temperatures speeds them up. Why? More kinetic energy, more collisions, greater probability of an effective collision with enough kinetic energy. What about concentration? So how does the amount of, let's say, the reactants influence the speed of a reaction? So typically, if you increase the concentration of reactants, you're going to increase the number of collisions just based on probability. So if you have one of each type of reactant, you have the probability of one possible type of collision. If there's, let's say, 2 nitrogen and 1 oxygen, well, then in this case, you have 2 possibilities, 1 from each nitrogen. If you have 2 of each, now the probability goes up to 4, because each nitrogen can collide with each oxygen and vice versa. So more collisions, the greater probability of an effective collision, so it increases the reaction rate. So an increase in the number of particles is going to increase that probability of collisions. How does a catalyst speed up a reaction? Well, typically what a catalyst does is it actually lowers this activation energy. So again, the activation energy is the minimum amount of energy for a reaction to take place. So it can lower it. And the other thing about catalysts is because it's actually not part of the reaction, it doesn't get used up. You don't even write it in the equation. People are typically comfortable when they think of catalysts with biological catalysts. That's what enzymes are. They're proteins that in the body, they speed up reaction rates, okay? So many reactants are thermally sensitive, and increasing the temperature can actually destroy them. So how are you going to speed up a reaction if you can't speed up the temperature or the temperature is constant? You can use a catalyst. So most reactions, those biochemical reactions that take place in your body, you have to maintain a certain body temperature. So you can't increase the temperature. So how can you speed up a reaction? Well, we're going to use enzymes, which are biological catalysts. So how does an enzyme lower the activation energy? Here's an example of sucrose, which is a disaccharide broken down to the 2 monosaccharides of glucose and fructose. So essentially how this occurs is we have an enzyme called sucrase. If you ever look at enzymes, they always tend to have the ACE ending. So lactose is a disaccharide, and you can break it into 2 monosaccharides, galactose and glucose, through lactase. So sucrose is broken down by sucrase and produces glucose and fructose. Now, how does that occur? Well, essentially, what an enzyme does is it has a particular active site where the substrate sucrose can fit in. And that puts it in the proper orientation that I was talking about earlier for effective collisions. So if it's in the proper orientation, now it's much easier to break the bond. Now, why is that? It puts it in a allosteric position where now this bond is easily broken. So catalysts, enzymes, they lower the activation energy because there's less energy required to break the weakened bond due to the position that the substrate or the reactants sit in the active site. So if you have an effective collision, basically that means the bonds are going to break in the right orientation. The enzyme puts it in the right orientation and weakens the bond to make it easier to break. So what are some of the biological enzymes that we're talking about? So lactase breaks down milk sugar, lactose. So people who are lactose intolerant lack this enzyme. Peroxidases, they break down poisonous peroxides. The lack of acetaldehyde dehydrogenase is what causes that red alcohol flush when people drink, because many of them lack this enzyme. They don't know how to break down the alcohols. Another factor that can increase the reaction rate are essentially all of these combined. So I can add more reactants, which involves more collisions. So I'm going to have more effective collisions and speed up reactions. I can increase temperature, more collisions with more kinetic energy. So that definitely is the energy required to break the bond. And then I can add a catalyst to lower the activation energy. So all three of these can increase the reaction rates. So let's look at sample exercise number 1 and see whether this change is going to affect the rate of the reaction. So is it going to increase the reaction rate, decrease it, or really cause no change? Because that's a possibility. So if I increase the temperature, typically that's going to increase the reaction rate. Why is that? Again, an increase in temperature, particles are moving faster. If they're moving faster, there's more collisions. If there's more collisions, there's a greater probability that those collisions will have enough kinetic energy to break the bonds, or there's just a greater probability of having an effective collision. Removing some of the reactants. Well, if I decrease the concentration of reactants, I have fewer particles. If I have fewer particles, there's fewer collisions. If I have fewer collisions, this is going to decrease my reaction rate because there's fewer collisions. Adding a catalyst always speeds up your reaction. Placing the reaction flask in ice. Well, it's the same concept of why we put food in the refrigerator, because it decreases reaction rates. It slows down the process of spoiling. Increasing the concentration of reactants. Again, more reactants, there's more particles, more collisions, resulting in a greater probability of an effective collision with enough kinetic energy and the right orientation for the reaction to take place. So let's look at this particular example. So we have 2 moles of carbon monoxide combining with 1 mole of oxygen to give 2 moles of carbon dioxide gas. What would the effect have? Would it increase, decrease, or not change the reaction rate at all? So again, if I'm raising the temperature, that's going to increase the reaction rate. If I take away some of this O2, there's fewer of these particles to collide with carbon monoxide. So that's going to decrease the reaction rate because I need more collisions. So removing O2 decreases the reaction rate. So a lot of this is conceptual. We haven't done any of the calculations yet. We're just focusing on collision theory and reaction rates. Adding a catalyst speeds up the reaction. Lowering the temperature decreases the reaction rate. So that's sample exercise number 2 with a more specific example. That way, instead of just saying reactants, I can be more specific and say, for example, in this case, oxygen. So what is equilibrium? Really, because equilibrium's the bulk of this chapter and this discussion in chapter 10. So most chemical reactions do not go in one direction. That's what it's hard for people to understand, that we always draw the arrow in one direction, and reactions don't go all the way until all the reactants are used up. In fact, most of the time, reactants aren't completely gone, and the reactions themselves are reversible. Think about all the reactions that occur in your body. They are reversible reactions. So you actually have a forward reaction and a reverse reaction. So you could have things go in both directions. The reverse reaction is when you produce products and it goes in reverse and produces reactants. So how do we show this forward and reverse reaction, or what is termed equilibrium? We use double arrows. So whenever you see double arrows, that means equilibrium. We've introduced this concept when we talked about weak electrolytes and how weak acids and bases, which are weak electrolytes, only partially dissociate, and that the majority of the time they don't break apart. You have a small quantity. That's where we introduce the double arrow to show that it doesn't go completely in one direction. So how does that look in terms of the rate of the reactions? Okay, so in equilibrium, initially the rate of the forward reaction, right? So if you're thinking of the forward, you would have your reactants, okay? So initially, you're gonna have a forward reaction to produce your products. And that reaction rate, if I look on this axis, the rate is increasing here, and this is over time. Initially, I'm gonna produce a lot of product. As more and more product begin to form, they begin colliding, and the reverse reaction begins to take place to produce now reactants. So we can see initially there's no product, so this reverse reaction, it doesn't occur, it's at 0. And the forward reaction, so this is my forward, this is my reverse. The forward reaction is very fast because there's just reactants colliding to produce product. As time goes on and I lose some of my reactant and I produce more product, the forward reaction begins to slow down where it stabilizes. With the reverse reaction, what starts to happen is at first, there is no reverse reaction because there's no product. Eventually, as product starts forming, it starts colliding, and eventually it reaches a stable, what's referred to as rate of equilibrium. Sorry about that. So I'll go ahead and erase this. So as more products formed, the rate of the reaction for the reverse reaction begins to speed up, as we can see in this portion of this graph. When the rates of the forward and reverse reaction are the same, that's when they reach equilibrium. So when their reaction rates are the same, it doesn't mean I have the same amount of reactants and products. It just means that the forward and reverse reaction are occurring at the same speed. When that occurs, I have what's referred to as a dynamic equilibrium. It's dynamic because it's constantly happening. You constantly have reactants producing products. You constantly have products producing reactants, but because they're at the same rate, it maintains the concentration of both sides. One of the requirements for dynamic equilibrium is to have a closed system so that whatever you produce can't escape out and it stays within that system. So here's kind of an analogy of a reaction and the reaction rate. So we have hydrogen gas, and we can say that the hydrogen gas is right there, the two little white space model balls right there. And then we have iodine gas, which are the larger diatomics in blue. Okay. The forward reaction would produce, oh, sorry about that, I'm a little messy. The forward reaction would produce the two hydrogen iodides. The hydrogen iodides are obviously the one iodide, which again is the blue, and the one hydrogen, which is the white. Okay, so again, this is my H2, this is my I2, and in this example, this would be my HI. So initially, the reaction vessel in this particular example, if I look, it has 4 of each. It has 4 hydrogens, 1, 2, 3, 4, and 4 iodines, 1, 2, 3, 4, and it has no hydrogen iodides, because initially, if I just put it in the container, I have just concentration of reactants. So as a result, my rate of forward reaction is very high. Eventually, some of these are going to collide and have an effective collision. So they're going to not only have enough kinetic energy, they're going to collide with the proper orientation. Not always, okay? But eventually what will happen is I will form a few of the products. So now in this example, you see that one of each hydrogen and one iodide collide to produce 2 of the hydrogen iodides. So now I have a concentration of 2 of my products. And initially I started with 4 and 4, but now I only have 3 and 3. So for the rates of the forward and reverse reaction, what you notice is the arrow for the forward direction has decreased a little bit. So in that previous slide, it's going down a little bit. And now the reverse is slightly building up because now I have a few of these that can actually start reacting as well. So the forward reaction begins to produce the HI, that's that second slide. And as the reaction proceeds, there's less H2 and I2, hydrogen and iodide, there's 6 versus 8. And I begin to produce and increase the rate of the reverse reaction. So now that I have 2 of the hydrogen iodide, I can produce this. At equilibrium, the concentrations of reactants and products are constant. So if I was to keep going on, right? So right now I have 3 iodine and 3 hydrogen. If one of each of these collide again, now I would only have 2 hydrogen, 2 iodide, but I've made 2 additional hydrogen iodides. So now I'm at 4. So I'm at 4, 4. And we see that the reaction rate in the forward direction is beginning to slow. Why? There's fewer collisions of the reactants. Why? Now I have products that are actually in the way. So here are 4 of my products, and they're going to begin to collide with each other as well. And as they increase their collisions, the reverse rate goes up. The reaction is going to continue, and it's going to establish what's referred to as an equilibrium. So when I talk about equilibrium, I don't mean I have equal amounts of reactants and products. Equilibrium means the rate of the forward and reverse reaction are the same. So at equilibrium, once that's established, you can see in this example, I only have 2 of the reactants. I have 1 hydrogen molecule and 1 iodine molecule. And I've actually produced 6 of the hydrogen iodine products, okay? As time goes on, this concentration does not change, but I still have movement. So you can see here specifically, I have, for example, these 2 may have collided and produced 2 of the hydrogen iodide, but now 2 of the hydrogen iodide collided and reverted back to the original reactants of iodine and hydrogen. So what's occurring is a equal rate of both the forward and reverse reaction. So I don't have equal amounts of reactants and products, right? I have 2 versus 6, but that ratio will be constant. So how are we going to determine that ratio of concentrations during equilibrium? So when there is an equilibrium, equal rates of forward and reverse reaction, how are we going to determine those concentrations? That's where we develop what is referred to as an equilibrium constant. Our equilibrium constant is based on the actual reactants themselves. So A and B represent reactants, and the products, C and D, represent the products, and then the lowercase a, b, c, and d represents the coefficients in the balanced chemical equation. So what we actually can do is create what's referred to as an equilibrium constant, which is a ratio of the concentrations of the products and the reactants at equilibrium. So typically what I tell students, when you're thinking of your equilibrium constant, so K stands for your constant. So sometimes they write in subscript EQ or C for concentration. I want you to always think, when you're thinking of your Ks, products over reactants. Okay, I just want you to remember that as a quotient. My product concentrations over my reactants. However, we won't neglect to remember that the balanced equations, the coefficients, we're going to actually use those as exponents in this quotient for the chemical equilibrium constant. Okay, so here's just an example of how I would write an equilibrium constant. So in this equation, I have 2 moles of dinitrogen pentoxide gas producing 4 moles of nitrogen dioxide and 1 mole of oxygen gas. So we don't write a 1 here, but it's obvious that it's 1. Otherwise, we wouldn't have even written out the formula. So now, to write out the K, what am I going to do? Well, it's, what did I say? Products over reactants. Okay. So in this equilibrium expression, the nitrogen dioxide and the oxygen are products. So I put those in brackets to show that this equilibrium constant or quotient is dependent on the concentration of the products over the concentration of the reactants. So the dinitrogen pentoxide is my reactant. But I also have to take into account these coefficients. So those coefficients I'm going to use as exponents for the concentrations. So for products over reactants, there's 4 moles of nitrogen dioxide. So the 4 is an exponent for the concentration of nitrogen dioxide. There's 1 mole for oxygen gas produced. So I just need to write the brackets because we already know that if I don't write a 1, it's implied. For the dinitrogen pentoxide reactant, there's a coefficient of 2. So I would make sure to put a 2 as the exponent because of that coefficient. So that is how we can write out what is referred to as an equilibrium expression or constant. And we're going to later plug in values in our later examples to figure out what that constant is and the concentrations of the reactants and products when equilibrium is established. Equilibrium not meaning equal amounts of reactants and products, but equal rates. But what we first have to do is practice. Just if we see a balanced equation, can I write out this expression so when I have those concentrations, I can plug them in? So our first example is, all right, what are we going to do? We have a balanced equation, and I want to make sure to write out K. Again, what is K? K is products over reactants. Okay, so if I look, I have nitrogen and oxygen gas as reactants. They're each 1 mole in the balance equation, and they produce 2 moles of nitrogen monoxide. So the K, products over reactants. My product is nitrogen monoxide, but the coefficient of 2, I have to raise that concentration to that power. And then for my reactants, I have nitrogen and I have oxygen. And because they have coefficients of 1, I don't need to write the exponent of 1 because it's obvious. And if I had the concentration of these gases, I could plug these in and calculate my K of equilibrium. So it's basically that. I like to write it for you to show how I derived it, but then I also have right here it a little bit neater if you can't read my writing. So what about B? Well, same thing. My K of equilibrium or my Kc for concentration is what? Products over reactants. My product is what? Nitrogen dioxide, but I have a coefficient of 2, so I square that value, and then my reactant is N2O4. So that's that. So we are just simply practicing from a balanced chemical equation, writing out the correct equilibrium constant, which is basically a quotient of products over reactants. So now this is a little more complicated, right? We're not having these combination reactions or decompositions. Now we have kind of a single displacement reaction here. It's still the same thing. K equals products over reactants. What are my products? Well, I have the silicon tetrachloride. The coefficient is 1, so I'm done. I put the brackets to show the concentration. The other product is hydrogen gas. However, that coefficient means I must take that to the 2nd power. And then in the denominator, I put my reactants. So now I have silicon tetrahydride. And I have chlorine to the power of 2. And I get my equilibrium expression. So what we've been doing is we've been setting up, okay, our equilibrium constants. Now, I don't know if you've noticed, but in every example here so far, it has been all gases. That's how I've introduced this. And this is easy to understand because in dynamic equilibrium, one of the things I need is kind of a system that's closed. The reason why I need it closed is I don't want the gases to escape. That way, once I produce the products, they can react and go in the reverse direction. So I need to kind of contain it. So these have all been gases, okay, up to this point. Well, that's because I focused on what was referred to as homogeneous equilibrium. It was homogeneous, why? Because every phase was the gas, right? So I can gas, all of these are gases, okay? Every example, homogeneous equilibrium, okay? Well, what happens if the phases aren't all the same? It's a little bit trickier, but it's okay. It's referred to as heterogeneous. Why heterogeneous? Because now I have more than one state of matter. In heterogeneous equilibrium, it's still products over reactants. We still put the coefficients as exponents. The difference is pure solids and pure liquids are not included in our equilibrium expression. Why? Their concentration really doesn't change, right? There's so much of it. If it escapes to a gas, and some of it vaporizes, it's a significant amount of gas vapor because I'm going from nothing to something. But as far as the water itself, let's say, if I'm talking about water evaporating in a closed system, the amount of liquid water molecules is so substantial, the loss of just one or two as a water vapor is trivial. So we don't need to include it in the K of equilibrium. But for the gas, going from nothing to two is substantial. So why am I bringing this up? Well, in this particular decomposition reaction, which we've seen if you're in the Chem 100L lab, this is the reverse of the combination of the lime with your CO2 when you exhaled with a straw to produce calcium carbonate. But this is calcium carbonate, it's a solid. So here's my calcium carbonate. And if it's in a closed system, it will produce lime. Okay, so here I have calcium oxide and CO2 gas. The CO2 gas won't escape because it's in the closed system. So the K of equilibrium, again, is what? Products over reactants. But what's the only product we're including? We're only including CO2. Why? Because the concentration, whether it's at equilibrium or not for the solid, it doesn't really change. So it's like, let's just say it's constantly 1, so we don't write it in. The concentration of the calcium carbonate, which would be on the bottom, is constant. There's so much of it, it doesn't really change, that we just write a 1 as well. So we're only including the CO2 gas. So for heterogeneous equilibrium, basically in your reactions where you're asked to solve for the equilibrium constant, you include gases and aqueous phases. Those are the phases you include. You do not include solids and liquids. So, oops, sorry about that. So both the CO2 and the calcium carbonate, because they're solids, they're not incorporated into the equilibrium expression. So in this example, I do include the aqueous because there is a difference in there. So I basically have an insoluble salt in solution, right? So if lead 2 sees chloride, we know it forms a precipitate. And we know that because of solubility rules, okay? However, there may be small amounts that haven't come and collided to produce a precipitate in solution. Or when some of those precipitate out, a few may go back into solution. So there's actually a dynamic equilibrium because it's contained in the solvent of water. So to show an insoluble salts equilibrium, and for this class, we don't go into it too much. It's actually KSP, it's a solubility product equilibrium expression. But what you're gonna include are your aqueous phases, right? Because there's a small amount of this, so any change is substantial, but we will not include the solid because the majority of it is solid and it doesn't change, even if a small amount does dissolve. So for your equilibrium expression, products over reactants, we just write the ions in brackets and their concentration. And notice again, because with lead 2 chloride, there's actually 2 chloride ions, we have that exponent. And again, it's products over reactants, and that reactant's a solid, so we don't include it. You can think of it as like, this is all over 1, but we just don't include it. So in exercise 4, can we write the equilibrium expression for this heterogeneous equilibrium reaction. So again, K, what is it? Products over reactants. However, we do not include solids and liquids, but we do include gas and aqueous phases in our equilibrium expression. So my K for this reaction would be, let's see, carbon monoxide, it's a gas. I'm going to include it. The coefficient is 2, so my exponent is 2. On the reactant side, carbon, it's a solid. Its concentration, it doesn't matter, forward, reverse, it's pretty much constant because there's so much of it. I will not include this in the equilibrium expression, but I will include the CO2 because it's a gas. And there's my K. Let's try another one because the heterogeneous equilibriums are a little bit trickier. So here I have iron 2 oxide as a solid and carbon monoxide as a gas produce iron, solid, and CO2 as a gas. So what am I not going to include? Not going to include the solids. So my K, not including the solid, or if there was a liquid, the liquid, only the gases and aqueous, it would be CO2 over CO. So here's another example, right? So phosphorus tetrachloride yields phosphorus trichloride and chlorine gas. I'm not going to include what? Don't include solid and liquids, but I include gases and aqueous. So I'm not going to include the phosphorus trichloride. So my K is what? Chlorine products over reactants. And there I get, and there's no exponents because the coefficients are 1. Last but not least, here's a double displacement. So I have lead 2 nitrate, which is aqueous because nitrates are always soluble, 2 potassium iodide because group 1A alkaline metals are always soluble, so it's aqueous, produces 2 potassium nitrate aqueous because they're soluble, and 1 mole of lead iodide, but it's a solid, lead 2 iodide, because it's insoluble. That's because group 7A, the halides, are soluble except lead, mercury, and silver, PMS. So for my K expression, products, potassium, nitrate, and I'm separating them. Why? Well, because that's how they would separate over. And I guess I could just do the whole concentration. I'll make it a little bit easier. You don't have to separate it. You can just do KNO3, whatever that concentration is. And then over here, I'm going to have my lead to nitrate concentration and my potassium iodide concentration, but to the second power. All right. One more here. So the solids, they're going to cancel. And I'm just going to be left with the gases and aqueous. And if I look at this, K is products over reactants. But I don't have any products that are gas or aqueous. So how do I hold the quotient's numerator, right? How do I hold that place? I put a 1. And then for my reactant, it's oxygen, but the coefficient is 3, so it's to the third power. So you're going to need all of these abilities to write your equilibrium expressions so that we can actually calculate what K is, and also so that we can determine concentrations. So let's calculate some equilibrium constants. So in this particular example, I go back to the hydrogen and the iodine producing 2 moles of hydrogen iodide. So I'm given, okay, so now I'm not just going to set up my equilibrium constant quotient. I'm actually going to calculate the value of the constant. And the way I'm going to do that, I don't know if you remember when we first covered, concentrations, when I was talking about it, brackets basically mean molarity, moles per liter. Okay. So what I'm going to do is I'm going to set up my K, and for the hydrogen, I'm going to set up a concentration of 0.11. For my iodine, I'm going to set a concentration of 0.11. And for my hydrogen iodine, it's 0.78. So at equilibrium, when the reverse and forward reactions are at the same rate, the same speed, those are the concentrations. Now, again, look, the concentration of my product is greater than the concentration of my reactants, but the reactants are still present, okay? So it doesn't only go in one direction. All the reactants aren't completely converted to products. And even though the reaction rates are equal, the amount of reactants versus products can be different. So this is a closed system, okay? And we can clearly see that the concentrations are different. So we need to set it up. So your K of equilibrium is products over reactants. My product is the hydrogen iodide. It's to the second power because of the coefficient of 2. My reactants are my iodide and my hydrogen. So my hydrogen and iodide. Well, now what am I going to do? Well, now that I actually have numbers to plug into this equilibrium constant quotient, because that's what the equilibrium constant is. It's basically a mathematical quotient. I'm going to plug it in. So for the hydrogen iodide, I plug in the 0.78, and I'm going to square it. Why? Because the coefficient of 2 in the balanced chemical equation. And then for both my hydrogen and my iodide, I have 0.11, 0.11. When I do the calculation, I get an equilibrium expression because I need 2 sig figs. The reason why I need 2 sig figs, I have 2 sig figs here, 2 sig figs here, 2 sig figs. I know that 5.0 times 10 to the 1 is just 50. So if I wrote it as 50, it would be 1 sig fig. I could have done this and just did 50 with a decimal, because then that trailing 0 would count, and that would be 2 sig figs as well. A lot of times you'll see, and you'll see why as we do more calculations, we're going to use scientific notation because you get either really big exponents or really small. So you get really large Ks or really small Ks. So here is an example of where I want to use the K of equilibrium actually to solve backwards and to get a concentration of CO2. So I'm now giving you the concentration of the reactants right there, giving you the concentration of one of the products right here, but I'm asking what's the concentration of another product. The only way to do that is if I actually have the K of equilibrium. So how would I do that? I still set it up the same. Products over reactants. Both products are gases, so CO2, CF4. Over reactants, products over reactants, so COF2 on the bottom, and it's squared because of this coefficient of 2. And now whatever numbers I have, I plug in. So, or I can rearrange. So the way I rearranged this basically is I multiplied both sides by the reciprocal of this to get rid of it. So I multiplied both sides by, oops, sorry, incorrect. Got a little careless there. So what happens on this side, this cancels, and I'm just left with CO2. And then on this side, we can clearly see is my K of equilibrium, COF2 squared over CF4. You don't have to rearrange it algebraically. You could just plug your numbers in. You'll end up getting the same answer, but I like to rearrange things. So my K of equilibrium was 2. My COF2 is 0.255. That was given, but I can't forget to square it. And then my CF4 is 0.118. When I do the calculation, I see that the concentration of my CO2 is 1.100. It has 3 sig figs because 2.00 is 3 sig figs, 3 sig figs, 3 sig figs. And I add the unit of molarity because it's concentration. And we can see that the molarity units were given here as well. Okay. So for your sample exercise number 5, we're going to do everything that we just did. We're going to set up our equilibrium quotients, and then we're going to plug in our numbers to actually calculate the equilibrium constant itself. So if you remember, right, the K of equilibrium is what? Products over reactants. Okay, that's what we do. Now we make sure this is a homogeneous equilibrium. They're all gases, so every species, every product, every reactant is in the quotient. So I set that up. So my products, carbon monoxide, hydrogen gas, which is cubed. Why? Coefficient of 3 over methane and water. So now how am I going to solve for my actual value for my equilibrium constant? Well, they give me for CH4 methane, it's 0.13. For carbon monoxide, it's 0.18. For water, it's 0.53. And for the hydrogen, it's 0.28, but I can't forget to cube that. So I plug those in, just like I did, and then I perform the math, and I get my K as a 0.26. Now, you could put this in scientific notation. You could say 2.6 times 10 to the negative 1. That exponent in magnitude so small, it's not really necessary. It's kind of like that last example with 50, but if you want, you could. It's 2 significant figures because every concentration here is 2 sig figs. For the equilibrium expression in this course, you don't need to use units. There are units because all the molarities would not cancel in this example. Just to keep it easy, for the K of equilibriums for this course, you don't need to have the units. In other courses where you do these type of calculations, you actually do need those units. But for this introductory course, we're not going to have the units. So now we're going to look at the following equilibrium. So 2 sulfur dioxide, 1 oxygen produce 2 sulfur trioxides. But now you're given the K, and the K is 680. So they're saying, what if the sulfur dioxide concentration was 0.3 and the oxygen was 0.15? Can I figure out the concentration at equilibrium for the sulfur trioxide product? And of course, you can. K is always what? Products over reactants. So what are we going to do? We're going to set up our K. My product, this is what I'm looking for. SO3, sulfur trioxide. Why is it squared? Because the coefficient of 2 in the balanced chemical equation. I have O2 on the bottom, SO2 on the bottom because they're my reactants. The SO2 is the second power because the coefficient of 2 in the balanced chemical equation. So now it's a question of doing what? Plug and chug, right? So you'll see in this example, I don't rearrange it algebraically. You can. I just plugged it in. So I'm plugging the numbers in. And then once I basically square my 0.3, multiply it by 0.15, and then multiply whatever that product is by both sides, and I get a 9.18. But the SO3 concentration is to the second power. So I have to square root both sides, and I get the concentration from my sulfur trioxide is 3.03 molar, because the concentration units are molarity. And I have 3 sig figs because that decimal right there means that that trailing zero counts. So that's 3. I have 3 right here and 3 right there. So my final answer should have 3 significant figures. So I'll leave this lecture at that because we actually covered quite a bit. We still have another lecture for chapter 10, but in this first lecture, we covered collision theory, which essentially talks about for a reaction to take place, I have to break bonds so that I can form new bonds to make new products, okay? For bonds to be broken and new bonds formed, I have to have enough kinetic energy to break the bond, but I also have to have the correct orientation. Otherwise, they won't break. They'll just bounce off. Those 2 criteria, enough kinetic energy to break the bond and the proper orientation, is essentially an effective collision. And we call that minimum amount of energy required for a reaction to take place activation energy. And then we discuss what affects reaction rates, increasing temperature, increases the number of collisions, increasing concentration, increases the number of collisions. Catalysts, they lower the activation energy because they put it in the proper orientation. All those things increase reaction rates according to our collision theory and our understanding of effective collisions and the minimum amount of energy required. Then we said, okay, well, in reactions, they're not just one way. If there's a closed system that involves gases and aqueous states of matter in a reaction, we can actually have forward and reverse reactions in a closed system referred to as dynamic equilibrium. Why? Once we build up the products, they can begin to react with themselves to go in the reverse direction and produce reactants. Eventually, the forward and reverse reaction rate will be the same. It doesn't mean I have the same concentrations on both sides, just means the rate stabilizes. We then begin to talk about how do we set up these equilibrium constants, these quotients of reactants and products. And we did homogeneous equilibria, where they're all the same. We use gases, like in this example. And then we introduce heterogeneous equilibria that includes all the phases, but when we write out our K expression, we do not include solids and liquids because those are relatively constant. They don't change drastically in equilibrium, like in the case of gases and aqueous. And then after setting up our Ks of equilibrium, we actually use the concentrations, plug them into the quotients to solve for those K values. Once we understood how to calculate K, we can then use a K to determine an unknown concentration, as long as we have the concentration of the other compounds involved in the equilibrium constant. So next time, we will continue our discussion of the value of K and how the magnitude of it tells us in equilibrium what is preferred, products or reactants. And then we'll talk about stresses that we can put on equilibrium to cause shifts in different directions and force an equilibrium to go in one direction. So I want to thank you, as always, for watching the videos. I appreciate your patience, and I'll see you next time when we talk about Chapter 10, Lecture 2, the Chatelain's principles, along with determining the significance of our K values. Thanks so much for watching. See you next time.